another circuit object to talk about is battery. Let's define the battery. So a battery is a device that holds two conducting terminals at a constant potential difference through the power of chemistry. That's all that's going on. Standard battery, this is a 9-volt battery. You don't see these quite as often as like the AA and the AAA cylinder batteries. But in this case, the 9-volt battery, here's the two terminals. Chemical reactions happen in here to hold a difference, in this case, of 9 volts between the terminals. So one kind of looks like this, and they're shaped different so you can tell them apart and so that they can clip together. And one kind of looks like this. One is the positive terminal, one is the negative terminal. And we know that it's a 9-volt battery, so that means the potential difference it holds is 9 volts. When we're thinking about batteries and circuits, we have to think about where's the potential 0. So for point charges, we said, oh, the potential 0 will always be at infinity. When you're doing field theory, the potential 0 at infinity. When you're making circuits and devices, you can be a little bit more, you can put the potential 0 wherever you want. So it's more convenient to pick one of your terminals or one of your electrodes, make the potential 0 there. So in this case, we're going to say the negative side will be just called 0 volts. And if that's 0 volts, then this is at plus 9 volts. So potential is always a difference, but if you define a 0, then you can start defining absolute potentials relative to that 0. So let's think what's happening really in this region. Well, if we have 9 volts here and 0 volts there, we actually have an electric field in here. So every time you hold a 9-volt battery, you're wielding a little electric field between its terminals. And you can say roughly what it is. Well, it's about a magnitude of about 9 volts per centimeter right along that line. They're not parallel plates. It doesn't make a uniform field, but it does make some sort of a field. We can also think about the potential. Well, these are conducting electrodes, so they must have equipotential surfaces all along their surface. So here is the 0-volt equipotential surface. It's the surface of that terminal. And here is the 9-volt equipotential surface. It's the surface of that terminal. And we know then also that the potential is going to go down as we go along the field. So the 8-volt line is probably something like that. 7, 6, 5, 4, 3, 2, and then the 1. So we can actually do field theory inside of a battery if we really want to. So that is sort of a law of physics and chemistry, that the chemical reactions in here must hold these at a potential difference of 9 volts. What we're going to do now is we're going to break the laws of physics. Now, it's a little bit risky and scary to break the laws of physics. You never know what's going to happen. But we're going to break them somehow because we're going to set something up where two laws can't be true at the same time. The laws of physics and chemistry require that the terminals of the battery be at a different potential. But we also talked about how in a conductor, the surface has to be all at the same potential. Right? Because it goes, all the electrons will move to make the surface all be at a constant potential. That's in fact why each terminal on the battery has to be completely at 9 volts and completely at 0 volts. Okay? We're going to do this with a little bit larger battery so you can see it better. So this is a 12-volt battery. Here's its two terminals. So this one is negative, we can call that 0. This one's positive, we can call that plus 12 volts. And this is our metal. So this is iron wire. It's 75 microns in diameter, so it's about the diameter of a human hair. You can't quite see it very well in the video, but I promise you that there's wire there. How else would I do this? There is wire there. There's wire there, okay? So I'm going to take this metal wire and I'm going to place it across the terminals of the battery. So we're somehow breaking the laws of physics. We can't have this be at 9 volt or 12 volts, this be at 0 volts, and this all be at the same, because we're going to make one essentially large conductor. So let's see what happens when we do it. Okay? It's very exciting. Okay, here we go. I'm really going to do it this time. Okay. Here we go. What happens when you break the laws of physics? Oh, whoa. The universe gets very upset when you break its laws of physics. Let's try again. Maybe the universe was just having a bad day. Let's make sure that's really the outcome of this. So we bring it down. And is it going to be 0 volts, 9 volts, 12 volts? What's it going to be? The universe says, nope, can't exist, has to go away. So the answer is no. Apparently, you just can't do this. Right? So it's impossible. So we have to figure out what's going on. Well, as I alluded to in our discussion of what's happening with the metal plates in a capacitor, whenever something looks wrong in physics, there's always an answer. You can always figure it out. And almost every time, the answer is you deviated from your model. Right? There's always some condition. Anytime you say something, there's always a condition. There's always a model. Well, here we have once again deviated from our model. And the way we've deviated is that we are no longer in electrostatics. Remember, the surface of a metal has to be at a constant potential in electrostatic equilibrium. And in this experiment, we are no longer in electrostatic equilibrium. Let's look at the details of what happened when that wire burst into flames. We decided to apply delta V to a conductor. And clearly, somebody was not happy about it. So let's imagine, let's sort of zoom in on a piece of that wire. Draw it kind of like this. So it was a conductor, and it was a cylinder. And that's what we did. We attached it to a battery, so we forced this side to be at 0 volts, and we forced this side to be at 12 volts, based on our definition of the negative terminal being 0 volts. And what's going to happen? Well, we know that this is similar to when we talked about a conductor before. If you put it in an electric field, you have some E applied. An applied electric field from the positive to the negative terminal. And this was the E, sort of like the one that's between the battery terminals. Okay. When you apply that to a conductor, we know what's going to happen. If there's negative charges in the conductor, and in this case the free charges were negative, they were electrons, little negative electrons, they're going to feel a force that's going to make them want to move this way. So all the little electrons that are negative start to drift that way. And if you want to think about it this way, there's also little missing electrons. Sometimes we call them holes, although in a metal they aren't as important. But since they're positively charged, they feel a force that way. So the charges start to drift. Positive to the right, negative to the left. But then here's the difference, is because of the battery, the charges do not build on the ends. When the charges get here, they don't build up, they just fall into the battery. Okay. That's how it's physically different from sticking the conductor in just a uniform electric field. Now we're touching it to a battery. And at the battery terminals, chemistry wants to happen. And the electrons say, I'm not just going to sit here, I'm going to go complete the chemical reaction in the battery. Same thing happens here. The positive charges of the lack of electrons contribute to the battery. That's how the battery maintains a constant potential. So if the charges can't build up on the surfaces, no opposing field is created. There's nothing to make things want to stop. They just keep going. No opposing field is created. E applied, APP, exists inside the metal. Completely the opposite of what we learned about before. Before we said if you put this in just a uniform electric field, charges will move, E field will go to 0. Now we're saying that doesn't happen because the charges can't build up and create an electric field. You'll still have a potential drop. Since we have an E applied, there's the 11 volt line, and the 10, and the 9, and the 8, 7, 6, 5, you get the idea, 4, 3, 2, 1, down to 0. So this face is at 12, this is at 0, and the potential drops throughout the metal. And then finally, what you end up with then is you have a continuous flow of charge, which I'm down to the most important part, what we're trying to get to. I'm going to put it right here in this teeny little part right here, which is current. Current is a continuous flow of charge when you're not in electrostatic equilibrium. That's the reason this is different, is we're not in equilibrium here. That's why you can have an electric field, you can have a potential drop, and the result is that current flows. Charges flow in the form of a current. Here's a simple definition of current then. It is simply the steady flow of charge. So let's look at the definition, mathematical definition of current. I'll draw a wire, a conducting wire, in this case going all the way across the board. Like that. Okay. So this is conducting wire. So current, the symbol we use is I. And mathematically, the way you think about current is it's the charge per unit time across a plane. So if I look at a cross section of the wire, like this, like that. Oh, that was dumb. Okay. Cross section of the wire, and then I'll think about all the little charge carriers. So here I'll have a bunch of little positive charges. And if they are flying along at some velocity due to the electric field that's being applied, so there they go. Is simply the number of charges per unit time that flow across a cross-section of the wire. Okay? The area vector is not involved here in the simple definition of current. It's just letting you know that the way you keep up with the charges is you don't look at a point and say how many go through that point or past that point. You look at the cross-sectional area of the entire wire or the entire conduit for the current. Okay? When you're keeping up with that, there's kind of two kinds of current, sort of. There's the average current, which is just if it was changing, say, and you wanted just the average over some amount of time, that would just be delta Q, the amount of charge over some delta T that flowed in that time. So that would work if it's not quite steady. Maybe it's pulsing or something. You just wanted the average. Take a long time, count how many coulombs go across. There's also the instantaneous current. I instantaneous. And that's the derivative dq dt. If you had some expression for the charge as a function of time as it moves across the plane, it would be dq dt. I'm just showing you both of these. This is the same as your velocity. If you think back to mechanics, the average velocity of a trip is the total delta change in how far you go over the total time. The instantaneous velocity is really the velocity at a single point in time based on the derivative of the position time curve. Okay. There's another current we sometimes think about, and that's where you do take into account this area. That's called J. That's the current density. And it's literally, it's just the current per unit area. All right. The current per unit area. So here, actually, it is a vector. So if we have this thing that's some area and you have some current flowing at it, you got to give the area a vector like that. And J is a vector, the current per unit area that's flowing, and the direction of J is just the direction along the wire, normal to that cross-sectional area. So sometimes we think in terms of just the total current, sometimes we think in terms of the current per unit area. Sometimes in science and technology, something gets defined a stupid way, and we just can't change it. It would make sense to change it, and we just can't do it. One example is the United States and the metric system, or the old foot-pound system. We can't do the metric system. It's cost us entire space probes, and it doesn't matter. We can't switch. Another example is in current. One thing you must remember is current is the flow of positive charge. And almost all the currents you will think about in the real world are going to be electron flow in a metal wire. So let's look at a metal wire and make this very clear. Here's a metal wire. Okay? We say it has a current in this direction. The current flows this way, from plus to minus. But if I ask you which way are the electrons going, the electrons are going in the opposite direction with some velocity. Okay? Current is the flow of positive charge. Therefore, if you're talking about negative particles moving, they're going in the opposite direction. We call those particles the charge carrier. So if you're ever unsure which way real charges are moving or which way the current is going, if the charge carrier is negative, then it's opposite of the current. So here, the charge carrier is the electron. And you know that the electron is negative. Okay? So the electron should be positive, right? If we wanted to have sort of a nice, simple world where not so many negative signs flying around, back in 17 whatever, we should have made the electron be positive. But it's stuck, it's negative. All this time, we've never changed it. But it's really doesn't mean that always that's the case. You can have other kinds of current. Here, you can have a proton beam. That's a current. It can even be measured as a current. In a proton beam, you could say, here's I. Well, what's the velocity? It's going to be the same direction as the current, because the charge carrier is a proton. And a proton is positive. All right. It could even get worse. You can have things going in different directions. In a semiconductor, we keep up with electrons and holes. So I've mentioned holes a couple times, or missing electrons a few times. And in metals, it's not really that important. But in semiconductors, sometimes most of your current can be thought of as holes. So in a semiconductor, if the current goes this way, you can have little electrons flying around, and they'll go this way. And you can have little holes, little lacks of electron flying around, and they'll go that way. So the charge carrier in this case is electrons going one way and holes going the other way. Okay. But that's something to always keep in mind. Current is defined as the flow of positive charge, even if you're working in a metal where all the charge carriers are negative. We can't fix it, we're just stuck that way. I gave you the definition of current as dq over dt, or delta q over delta t, the charge per unit time. Now let's look at sort of the microscopic model of current. I've had students get confused about this. We end up with sort of many, many definitions of current. Seems like more than there should be. But they're all sort of in different cases. So what I told you before was the mathematical version of current. dq dt, that's if you have some function you're taking a derivative, maybe. Here, this is a microscopic model. That means we're really going to look inside at the charge carriers and see what they're really doing, and see if we can describe current in terms of how they're moving. That's a microscopic model. So here's the microscopic model. We've got to think about the flow of charge at constant velocity, which we're going to call v drift. Because if you think about it, if we're going to have a steady current, that's the flow of charge past this plane. And if that's going to be steady, it's always going to be the same amount flowing. All the charges, therefore, would just have to move at the same velocity in the most sort of simple, uniform idea. So let's draw the wire and again and see what it's going to look like. So here's the big wire. And we're going to go into dreamland and just pretend that the charge carriers are positive. Okay? So here we're going to use a new variable. We're going to use n. N is the charge carrier density. Okay? So there's all these charge carriers in this wire, and they're moving along with v drift, and they're moving with the current I. So we're going to pretend they're we're going to define them to be positive. And this is their density. And one thing to point out is that N, again, is the number of carriers per unit volume. It is not the same. It's not the same as rho. So remember rho? Rho was the charge density. You might say if it's the number of carriers per unit volume and they're charged, then it must be basically rho, that this wire is charged. Well, that's not the case, okay? Two reasons that's not the case is that one, when a wire carries a current, it's not necessarily charged. In fact, it's not charged usually. There's just as much negative charge as there is positive charge in a neutral wire. It's just one of the two, the charges can move, right? Even if they both move. Even if the electrons flowed one way and the protons flowed the other way, you could have a current flow and it would still be neutral. So don't mix these two up. If you actually need the number of carriers per unit volume and you need their actual charge, which we'll need in a minute, you have to multiply N by the charge on each carrier. If it's protons, then it would be multiply it by E. If it's electrons, multiply it by negative E. Okay? So N is literally a number here. Its unit is simply inverse meters cubed. There's no charge in N, okay, lowercase n. Okay, so let's think about our model. Let's see, I, the current, we said was delta Q, delta T. So now let's write that in terms of the microscopic model. So if we pick an area like this, we're going to think about the number of charges that go across that area. And in a unit of time delta T, all the ones that cross that area are going to get to a certain distance to over here. Right? They're going to make it to there. All right? So this is at T equals 0, and this is at T equals delta T, is how far these charge carriers are going. Well, if we know their velocity, then we also know how far they're going to go. They're going to go a distance delta x. And since we know their velocity, we could get the relationship as v equals dt. Okay? So now we're equipped to plug in for delta q and delta t. Okay? So the amount of charge is what? It's the density of charge carriers, number of charge carriers per unit volume, N, times the volume of this thing, right? This is how many flowed by in delta t. So the volume of this is A times delta x. So A is the end cap and delta x is the length. And that is not yet the charge. Right? That is the number. To make it the charge, we need Q. That's the charge of each charge carrier. Charge carrier per unit density, each has charge Q, little q. So each one of these is a little q. Okay? And let's see. So in the bottom, delta t is just delta t. Okay? So if we look, we can see constant, 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 and that is v drift, how far they go in a certain amount of time. So the microscopic model for charge is that it's N, which is the number, Q, their charge, A, and V drift. So we're going to use that as we think more about charge.